In this video, we're going to be looking at changes of state and the particle model. As you can see, this is the first of two videos for the particle model of matter topic. So, the first thing we're going to look at is density. Density of a material is how much matter there is per unit volume. This means how heavy a certain lump of particles are. For example, 1 meter cubed of copper has mass 8,940 kilograms, but 1 meter cubed of aluminium has mass 2,710 kilograms. Density is measured in kilograms per meter cubed. What is volume? Volume is how much space something takes up. It is a 3D measure. So, if you take this phone, for example, the volume of this phone is the amount of space this way multiplied by the amount of space this way multiplied by the amount of space this way. You can work out the volume of a shape with these formulas. If it's a cylinder, it's pi times radius squared times the height. If it's a cube, it's the length cubed. And if it's a cuboid, it's, as I've just shown you, the length times the width times the height. And I recommend learning these formulas for finding the volume of shapes, not only for your maths GCSE, but also for your physics GCSE, because if there's a question that regards density or volume, you need to know this in the exam, obviously. So we're going to have a look at our first formula for this topic. Mass is equal to density times volume. Mass is measured in kilograms, density is measured in kilograms per meter cubed, and volume is measured in meters cubed. So we're going to have a look at a worked example now. The density of a certain metal is 5,000 kilograms per meter cubed. The volume of this material is 2 centimeters cubed. Work out the mass of this metal. Okay, so this one's actually much more tricky than what it might first look. Obviously, first of all, we'll write out our equation. Mass is density times volume, and we plug our density in. Obviously, our unknown here is mass, but the volume isn't as straightforward as what you might think, because remember, our units for volume are meters cubed, okay? So our units for volume are meters cubed. But we're given our volume in centimeters cubed. Now, there are not 100 centimeters cubed in 1 meter cubed. That's not how it works. Because in 1 meter cubed, you have 1 meter times 1 meter times 1 meter. So you have 100 centimeters times 100 centimeters times 100 centimeters. So actually, what you get is 1 million centimeters cubed. So in 1 meter cubed, you have 1 million centimeters cubed. That means 2 centimeters cubed compared to 1 meters cubed is 2 over 1 million. Two over 1 million is 2 times 10 to the minus 6. Plugging that into our formula and evaluating that, we get that our mass is 0.01. And since mass is measured in kilograms, the final answer is 0.01 kilograms. It's very important that before attempting density questions, all of your units are the same. If density is measured in kilograms per meter cubed, then your units must be in kilograms for mass and meters cubed for volume. If density is measured in grams per meter cubed, then your units must be grams for mass and meters cubed for volume. If density is measured in grams per centimeter cubed, then your units must be grams for mass and centimeters cubed for volume. Complete task 1 in your particle model of matter workbook if you're following along with this in your workbook, and pause the video now. Okay, next we're going to look at the states of matter. There's 3 states of matter. Can you name them? Let's have a look at what they are. The first is a solid. Solids are materials which we can touch without the material moving around us. Solids are firm and stable in shape. Solids have particles arranged in uniform, and these particles have less energy than in other types of matter. So this diagram shows what the particles would look like and how they are arranged in a solid. As you can see, the particles are uniform, so they are in rows and they're in columns. They're not randomly arranged, and they are very close together. Liquids is next, and liquids are materials whose particles are spread out. Liquids have gaps between the particles, and most particles touch other particles. They semi-fill a container. So, this shows a liquid. Now, if you have this container around the outside here, you can see that the liquid fills the space, but if that container was much taller, the particles wouldn't spread out into all of the container. They would only fill the sort of bottom bit up. So they don't fully fill the container, but they shape themselves to fit the container. So as you can see, the liquid's particles are arranged non-uniformly, so there's not much of a clear row and column pattern here. Some of the particles are touching each other, but on average, the distance between the particles is just that little bit bigger than in solids. Finally, we'll have gases. Gases are the third state of matter. Materials in gas form completely fill their container and do not touch other gas particles. They bounce off of one another. Gas particles have the most energy. So out of the 3, gas particles and gas as a state has the highest energy. Liquids have medium and solids have the lowest energy. So this diagram shows the particles in a gas. You can see that the particles are all spread out. They are the lines behind show where they're coming from. So you can see that they are travelling in all different directions and they completely fill their container. Now, compared to liquids and solids, you can see that the average space in between the particles in a gas is much bigger as well. So, as particles spread out, they become less dense. And as you've noticed from those diagrams, as you go up the states, as you go from solids into a liquids, into a gas, the space in between those particles increases. So, that means the density decreases. Solids are the most dense. This is because for the same volume there are many particles. So if you take a volume of something which is in solid form, there'll be a lot more particles in that area than what it would be the same for that same substance if it was a liquid. Liquids have a medium density. This is because for the same volume there's less particles in that chunk, if you like. So if you take that same volume as you did for a solid but for a liquid, there'll be less particles in that volume, won't there? Because they're more spread out. So liquids have a medium density. They're not quite as dense as solids. Gases are the least dense. This is because for the same volume, there's even less particles. So if you take that same volume as what you did for your solid and you did for your liquid, there'll be even less particles in a gas because they are even more spread out. So gases are the least dense out of the 3. When you heat particles, they get more energy. So when you heat an object, particles get more internal energy. And this means they vibrate much more. And this is what we feel as heat. So if you touch something and it's hot, what it actually is, it's those particles having kinetic energy. It's those particles vibrating. And when you heat a substance up, you're giving those particles more energy. And those particles are vibrating more. There's more energy in its internal store. When you heat the materials, they collide with each other more and with more energy, resulting in them gaining distance from one another. This means there are gaps between the particles. So as we've seen from the diagrams, when you heat those particles up, the spacing increases, they get further apart from each other. These gaps are spaces and mean in the same volume there is less particles, making the density lower. So as those particles get more spread out, there's more space, there's more volume where there aren't particles, and essentially that means the density is going down because there's less mass within that volume. So you can change the state of matter in which a material is in. So going from a solid to a liquid, well, that's known as melting. Like if you have an ice cream and it melts, the ice cream becomes a liquid, doesn't it? It melts. If you go from a liquid to a solid, well, that's freezing. If you take water and you put it in the freezer, you're going from a liquid to a solid. You're going from water to ice. You are freezing that water. Going from liquid to a gas, well, that's evaporation or boiling. So if you go from a liquid, if you go from water to a gas, well, that's evaporation. The water evaporates into a gas. In the oceans, in the rivers, water evaporates and becomes a gas if it's a high temperature. Going from gas to a liquid, that's condensation. So if you are having a shower and you notice on the glass a sort of a mist appearing, well, that's actually the gas becoming water, because what's happening is the air particles, which are warmer, are hitting the colder glass, and when those particles hit the cold glass, they cool down, and when you cool gas particles down, they become a liquid. So that's condensation. So you only need to know these ones here. You don't need to worry about deposition or sublimation. I think that's further on if you study at A level or whatever. But solid, liquids and gas, you need to know these. You need to know melting, freezing, condensation and evaporation / boiling. So state changes, like evaporation, are physical changes. They aren't chemical ones. So if you study chemistry, you'll see that you can have chemical reactions, you can have chemical changes. If you take some substance and react it with something else, it makes a different substance. That's a chemical reaction. That's a chemical change. State changes aren't chemical reactions. They're not chemical changes. They're physical changes. Changes of state are physical changes which differ from chemical changes because the material recovers its original properties if the change is reversed. So if you heat up ice and it becomes water, you can cool it back down again and it'll become ice again. It's a physical change. Materials which are gaseous with a lower density rise. When materials are heated, their density reduces. This means heated gases rise above those which are cooler. So obviously gravity is a thing on Earth, and you find that things are pulled towards the centre of the Earth with mass. When you have something with a lower density, you have a lower mass per unit volume, because that's what density is, it's mass per volume. So if you have something with a lower density, what you find is, you find that it rises above gases with a higher density, because the gas with a higher density has more mass in the same volume. So that's pulled towards the Earth's centre more through gravity. So what you find is, you find that heat, because that has a lower density, it actually rises, and it rises above the gases which have less heat, which have a lower temperature. If you're following along in your revision workbook, pause the video now and complete task number 2. So there are 2 experiments which you can do to determine the density of objects. The first experiment for finding the density of regular objects, like cubes, and the second one is for finding the density of irregular objects, like a vase. For experiment 1, it is as simple as finding the mass using a mass balance and then measuring the sides of the cube. To find the volume, just use L cubed, or if it's a cuboid, length times width times height. Now use the formula density is mass divided by volume. So, just going over that again. If you have a regular object with length, width and height, and it's easy to measure, what you can do is you can find the volume by using one of the formulas that we've went over, and then you can use the density formula, which we've looked at before, to find the density, because you know the volume, you've just worked it out, and you know the mass because you can place it on a mass balance and find it. So the density is just the mass divided by the volume. For irregular objects, you need to use something called a Eureka can. This is a type of apparatus which tells us the volume of irregular objects. Firstly, you fill the Eureka can with water until the level reaches just below the spout. Now submerge the object into water and measure the amount of water which comes out of the spout. This is the volume of the object. Now use a mass balance to measure the mass and use the same equation. So, a Eureka can is, we're going to watch a video on this in just a second so you'll understand this a little bit more, but a Eureka can is a column of water or a sort of jug of water with a spout. And what you do is you fill that just to where the spout is, so the water doesn't come out of the spout, but just so it's level. And what you find is when you submerge something in that water, the volume of that object will displace the same volume of water. So if you have an amount of water below that spout and you put an object into that water, that object will take up the volume that the water did, and it will displace that water. It's got to go somewhere, hasn't it? So if the water's just below the spout and you put an object into the water displaced will be forced through the spout and into a measuring cylinder. And if you use that measuring cylinder, you can work out the amount of water displaced. And the amount of water displaced is just the volume of the object which you have submerged. So if you have an irregular shaped object, you can submerge it in water, and the amount of water the amount of water displaced is the volume of that object. This is what a Eureka can looks like. So you would submerge the object into the water, and the water would be filled just to this level here, so it's just below the spout. And when you put an object into that water, the water will rise, travel through the spout, and the amount of water which comes out of that spout is the volume of the object which you put in. So the amount of water displaced is equal to the volume of the object which has been placed in the water. So we're going to watch a little video now about doing this experiment. Hello there. We're going to be determining the density of objects. This is a required practical, and for this required practical you will need an object to measure the density of, a balance, a Eureka can, a ruler, and a measuring cylinder. In order to work out an object's density, you need to know its volume and its mass. This is because both volume and mass appear in the equation to calculate density. There are two possible scenarios. The first scenario is that our object is uniform, i.e. its dimensions are easy to measure, for example a cuboid. Alternatively, our object could be irregular, i.e. its dimensions are too difficult to measure, for example an ornament. In both scenarios, we start by measuring the mass of the object. Do this by placing our object onto the balance. Record the mass of the object. Once we have the object's masses, we need to work out the volume of our objects. For objects of uniform shape, this is very simple. Measure the dimensions, the width, the height, and the depth, and then multiply your results together. Converting from centimetres to metres is very important at this stage. Our measurements of the cuboid are 60 centimetres, 30 centimetres and 15 centimetres. Converting into metres, we have 0.6 metres, 0.3 metres and 0.15 metres. Multiplying our numbers together, we'll get a total volume of 0.027 metres cubed. For our irregular object, we need to use a method called displacement. The volume of water an object displaces when submerged is equal to the object's volume. We can use a Eureka can, an object with a bath of water and a spout, to measure the amount of water displaced, and hence the volume of the object. Place a measuring cylinder at the end of the spout, so we can measure the volume of the water displaced. Once the object is fully submerged, make a recording of the object's volume by measuring the volume of water in the cylinder. The cylinder may use units which we commonly use to measure liquid volumes. 1000 millimeters are equal to 0.001 meters cubed. Here is the equation for density with relation to mass and volume. Density is mass divided by volume. Since we are looking for the density, there is no need to rearrange. Let's use the example of our regular object. The following also works for our irregular object, the ornament. Here are some values from our practical. The object's mass was 0.215 kilograms and the object's volume was 0.027 meters cubed. Plug in those numbers into our formula and we'll get that the density is 0.215 over 0.27. Evaluating our equation, we get that the object's density is 7.962 kilograms per meters cubed, and that is how you calculate the density of objects. So that's just went over what we've previously went over there. Just a quick note, the equation which we used to calculate the volume of that regular object, if that object was a cylinder, we would use the equation for a cylinder. If it was a sphere, we would use the equation for the volume of the sphere. If you have a regular object, you just need to adapt whichever shape it is to the equation which hopefully you've memorised. It doesn't have to be the length times width times height. Internal energy. Energy is stored inside a system by the particles, atoms and molecules, that make up the system. This is called internal energy. Internal energy is the total kinetic energy and potential energy of all the particles, atoms and molecules, that make up a system. That's something that you need to know, what the internal energy is. What happens when energy is put into a system? When objects gain energy through heating, they can do one of two things. Energy is either used to fund a change of state or to heat up the substance. Complete task 3 in your particle model of matter workbook. Okay, so I'm going to be honest with you, this next part is quite boring. It is the specific heat capacity. Now this one's a little bit funny because specific heat capacity comes up in both the energy topic and the particle model of matter topic because it's kind of related to both. So if you're feeling confident on the specific heat capacity, you don't need to watch this bit, but it is quite tricky and it is part of this topic as well. So if you've watched the energy topic and you're happy with the specific heat capacity, don't worry. But if you haven't watched the energy video, or if you're studying for a particle model of matter test or something like that, then I would watch on. So the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. Yet another formula is given from this. However, you do not need to learn this formula as it is given to you on the day of the exam. If you know the change in thermal energy, the mass, and the temperature change, you can work out the specific heat capacity, and that is because delta E is equal to mc delta theta. The change in thermal energy is equal to the mass of that object multiplied by the specific heat capacity multiplied by the change in temperature. Change in thermal energy is given in joules because it's an energy. Mass is given in kilograms. Specific heat capacity is given in kilograms per... Sorry, no it isn't. It's given in joules per kilogram degrees Celsius. And change in temperature is given in degrees Celsius. Let's look at a work example. Lead is a metal used in making salt. Salt must be processed in a heated environment with a minimum temperature. Lead has a specific heat capacity of 1,600 joules per kilogram, per kilogram degrees Celsius, that should say, and requires 300 joules to heat up the temperature. If the mass of metal used was 40 kilograms, how many degrees did the block heat up? So the first thing we're going to do is write out our equation. Delta E is equal to mc delta theta, or change in energy is equal to mass times specific heat capacity times change in temperature. So our unknown value here is the change in temperature. That's what we want to work out because it asks by how many degrees did the block heat up. So firstly, we're going to divide both sides of our equation by 40 times 1,600. If we do that, we get 300 divided by 40 times 1,600 is equal to our change in temperature. Evaluating 40 times 1,600, we get 64,000. 300 divided by 64,000, well, that's 0.0047. So our change in temperature in degrees Celsius is 0.0047. We're going to watch a little video now about the specific heat capacity of a material and how to measure it.
Hello there. We're going to be calculating the specific heat capacity of a material, and this is one of the required practicals. So for this required practical, you will need a beaker, a balance, a material to measure the specific heat capacity of, and in this example we'll be using cooking oil, an immersion heater, thermometer, bubble wrap / thermal wrap, joule meter, power pack, and a lid for the beaker. Okay, so we're going to start by placing the beaker onto the balance. Press the 0 button now, so any mass which you add on top of the mass of the beaker will be counted only. Fill the beaker with oil and record the mass of the oil. Next, place a thermometer and an immersion heater into the oil. You need to record the initial temperature of the oil as shown on the thermometer before we add any heat to the oil. Now we'll place our insulating material around the outside of the beaker and place an insulating lid on the top. Connect your immersion heater to a joule meter, a device which records the electrical energy transferred, and a power pack. You now need to wait for 20 minutes, and once this time is up, you need to record the measurement on the joule meter. Also record the new temperature of the oil using the thermometer. Here is the equation for energy transferred with relation to specific heat capacity. Energy transferred is mass times the specific heat capacity times the change in temperature. Now we want to find our specific heat capacity, so we need to rearrange this formula. Once we've rearranged it, we get that the specific heat capacity is the energy transferred divided by the mass multiplied by the change in temperature. And here's some values from the experiment. Initially, the temperature was 20 degrees. In the end, the temperature was 43.23 degrees, and the mass of the cooking oil was 0.54 kilograms. 20,706 joules of energy entered the system. So we're going to plug all those numbers into our formula. We have the 20,706 divided by 0.54 multiplied by the difference of 43.23 and 20. Evaluating our equation, we get that our specific heat capacity for the cooking oil is 1,651 joules per kilogram degrees Celsius. Now, in the exam, you could be asked about potential sources of inaccuracy. One source of inaccuracy is thermal energy or heat escaping the beaker through the gaps in the lid or through travelling through the insulation. Another source of inaccuracy is that the energy being converted from electrical energy isn't all passing into the oil's thermal energy store, especially if the immersion heater is sticking out of the liquid. And finally, the thermal energy may not be spread into all parts of the cooking oil. To help this, you should stir the oil.
Okay, so again, that is a required practical, so I would recommend learning the details of that. And that end bit there, that's very important because in the exam they often like to ask you about inaccuracies and where errors can come from and things like that. So again, I would just learn that. Okay, so if an object is harder to heat up and takes more energy for the same mass, does it have a high or a low specific heat capacity? Well, the answer is it has a higher specific heat capacity. So if an object is harder to heat up and takes more energy, then the specific heat capacity is higher. Complete task number 4 in your particle model of matter workbook if you are following along.
Thank you very much for watching. Workbooks
and test papers which integrate with these videos, and online courses are available at our website, backroadtutoring.com.